Okay, so here we have plotted the symmetric vibrations of the drum where there's no angular variation. So the first three modes are displayed here. They're animated as a function of time. And actually these movies, these GIF files, are taken directly from what's available on the web. If you look for drum vibrations, you'll find a Wikipedia link, and these movies are directly downloaded from there. And what we have done here is to make it just slightly more realistic than what you will find there. Is the idea that higher modes vibrate with a higher frequency, and that we have sort of incorporated here in this visualization. And so you can see that the lowest order mode, the first mode of vibration, essentially either has a peak or a valley or depression. This is the oscillation which you would have if you tap in the middle of the drum. So the center has the largest displacement, and everywhere else monotonically that displacement goes down to 0 at the rim. Mode 2 has one nodal circle where there is a 0 level, and between inside and outside the phase of oscillation changes. So if it is positive inside, it's negative on the outside. So meaning if it is displaced outward inside, then it's displaced inwards on the outside. And so that's the sort of shape that you can visualize there. And at any time, if we take a cut and plot that as a function of radius, we would see the radial shape that we have talked about in terms of the Bessel function J0 with the multiplier in the argument that we had. And finally, the third mode, as you can see, it oscillates even more rapidly, and it varies more rapidly with respect to its radial shape as well. And so that is what we can see. Everything is finite at r equal to 0, and we have these shapes. And so hopefully you'll remember these shapes of Bessel functions. Here we can see the Bessel functions coming alive in this example. Of course, Bessel functions show up in other problems, not necessarily of vibrations. They show up in oscillation problems, but they also show up in diffusion problems. Heat conduction in a cylindrical rod or mass transfer in a circular geometry also involve Bessel functions. And so these shapes have more to do with a broader range of problems also. Okay, so we are now animating the shapes of vibration of a drum head under more general conditions. So these are non-symmetric vibrations that have angular variation. And so these correspond to the azimuthal index that we had in the analysis, denoted by the math symbol m, integer m, m equals 1. These modes are visualized here, and so going from left to the middle to the right, the mode number associated with n, which has to do with which 0 of the Bessel function is associated with these shapes, is changing from 1 to 2 to 3. So the leftmost here corresponds to n equals 1 and m equals 1. The second one corresponds to n equals 2 and m equals 1. And the last one is m equals 1, but n is now 3. And so as we go to higher modes with given azimuthal order, so if we call m the azimuthal order, m is equal to 1 in all of these cases. So at a fixed azimuthal order, as we go to higher modes, the radial variation becomes more rapid, and oscillation frequency also increases as we go to higher modes. And you can see the shapes here is that as we go around the azimuth, when the azimuth index is equal to 1, we essentially have one cycle of oscillation. So it starts with, say, a positive number, and well, we can start with 0, it increases to a positive number, it comes back to 0, then goes to a negative number as we go around the azimuth, and back to 0, and so on. So that's the pattern at any time. If we take a snapshot and look at the variation going around the azimuth, that is the variation that we would have, and that's associated with sine m theta variation that we have sine m pi theta, and so m is an integer, and that integer here is 1 for these modes. And so we will now contrast these with the next azimuthal order, which is m equals 2. So here we have drum vibration shapes for the azimuthal index 2. So these are non-symmetric vibrations. They have azimuthal variation, as you can see. And as we go from left to right, we are increasing the radial order, if we can call it that, which has to do with which zero of the Jm Bessel function is being used to define the shape of this natural mode shape. And so for each of these, we can see that if we go around the azimuth, we have 2 cycles of oscillation, 2 complete cycles. So starting from a value of 0, if we increase and go through one period of oscillation, we will go through one more period of oscillation, 2 complete oscillations before we come back to the same phase. And so that is reflected in the patterns that you can visualize as they hop up and down and so on. When their peaks are rising, we will see that there are 2 peaks and 2 valleys at the same time as we go around the azimuth. And with respect to radial structure, the leftmost image has no interior nodal line for some finite radius, but as we go to mode 2-2, the middle picture, we have one radial line where the activity vanishes, and when we go to the last, the far right there, we have 2 radial lines where the activity vanishes and so on. So as you can see, the complexity in terms of the azimuthal and radial structure of these modes enriches, becomes more complex as we go to higher mode numbers, so both in the azimuthal order as well as radial order. Frequency increases as we go to high azimuthal and radial mode order. And we can also say that if you have any general initial condition, or given the drum, if we hammer on it in an arbitrary way, any way that you may want to imagine, the solution or the response that that drum has can be synthesized as a superposition of these various modes that we have talked about, which have different frequencies and different shapes. And there is enough richness in these shapes to be able to synthesize an arbitrary function, or an arbitrary displacement over the drum head can be synthesized as a sum of these shapes that we are seeing. So this is a complete description. When we take enough of these modes, we can describe any arbitrary variation and so on. And so that's a very powerful result that we have available, and modes of this kind can be used in other problems besides vibrations, as we have talked about. And so in closing, what I would like to mention is that on the internet, there are many resources that you may want to look into. People have been curious about seeing how well this simple mathematics that we have described actually represents the vibrations of a real drum and so on. And there are interesting articles you can find where people have measured the actual vibrations and made comparisons to this analysis, and there's some commentary and so on. So if you're curious about this, look into it more, and then hopefully that will give you some further ideas and may direct you to things that you can learn further about and so on. Of course, the drum vibration frequencies and shapes depend on the shape of the drum. So if you think about a drum shape which is not circular but elliptical or some other shape, then that also naturally reflects in the frequency and mode shape of vibration. And so you can think about that. And there is a natural analog between such things and vibrations in quantum mechanics, the quantum numbers and the spectroscopic implication of that when we use diagnostic techniques to be able to discern when we carry out a test what a species is present, and we can infer it through various scattering techniques and so on. We are essentially relying on the connection between that specific vibration and the eigenfrequency associated with it.